Physics.
It's going to involve you guys in your detector groups. And then I'm going to give you data from your detector.
Yes.
And then with that data, you're going to analyze it and figure out, you know, what you got, like what you saw. No, I'm not going to give you millions of events. You don't have that kind of time. Yes.
Is it possible to use programming to analyze?
Is it possible to use programming? Of course it's possible.
Yes.
Yes.
I'm going to grab something from when I'm at the
I mean, they don't exist, so no. But the data you are going to get is going to be simulated based on the geometry of the detectors that you have made. Oh. So I'm going to take that spreadsheet for the final detector, and I'm going to plug that into a program I have, and it's going to generate data. Yeah. I mean,
never mind, I can't use things.
Because, as I love doing, I'm going to have, at the end of the day, individual assignments for each person. And so it will not be, so as I tend to do, it will be kind of a group project without a group grade. Yeah. It'll be those final detectors. Otherwise, I have to deal with the accelerator in space. Yep. Yeah, it'll be things like, well, it won't be clustering. It will be like clustering, which is not what you've done. It'll be like, here's a bunch of hits in your detector. Figure out what happened.
I'm suddenly very glad my detector didn't get through because that would have been insane.
I will give you some details and
because I suck.
Maybe some samples to work with. Hopefully, actually, I think it's going to be okay with that.
I've heard it before.
But that will come, and that will come. Might be kind of close to the final, but it's still better than like never happening, right?
So are we only about?
Do we have a test?
Can I give us a quiz?
I mean, you'll all be in the same place. It's in N2, by the way. Finals Thursday afternoon in N2. Thursday at like 2:30, is it? I think it's 2:30 at N2. Still not quite decided that. I am aiming at, last year I aimed at 10%. No, I achieved it. Last year was 10%, which was fine. But this year I'm still excited. I think it might depend when I look at your actual grades. Yeah?
Does the final normally have a positive or a negative effect?
That's an interesting question. Normally is a funny word. I've only done it once before. When I did it last year, the effect it had was positive, but most of that was out of pity. So, I mean, you know, pitiable is not a constant word to use. So,
if it means just getting better points for the final, goodbye.
So the main reason was I thought they had a good argument that there was a limited amount they could do in an hour and a half, right? So if I give you guys a little bit more warning, which I just did, then that means I have higher expectations, right? So like I said, I will give you more details as I come up with that. I'm just telling you where I am right now. So the point is, the main reason I'm doing this is I do not want you taking time that you could be using to write papers, do projects, or study for your other classes, study for things you don't need to study for in this class. I do not want you to do that. So I can tell you that you do not need to study for most of this class, right? The only thing you really might need to know that I can think about that you shouldn't just already have stored away or within your notes easily accessible or on the internet is possibly relativistic kinematics. And that will, because that matters, right? Collisions and stuff like that, that will matter. But I will try and give you some more details on that as well. But the point is, I don't want you blowing a lot of time studying as though it were an exam. That was actually my biggest regret about not telling them, is that people spend a lot of time studying like as if it were an exam like we just took, and it's not, right? And so I want you to use your time wisely. Time is short in December, so I want you to, days are shorter. So no, I mean because you have a lot to do, so I want you to be able to allocate your time wisely. Okay, so I don't intend for this to have a large preparatory component, right? I intend for it to be fun. It was fun last year, anyway for me. So So, that being said, let's talk about something actually fun. All right, cool. All right?
Feynman.
So today's topic is death. Well, not exactly, sort of indirectly. Let's start by talking about radioactivity, which is related, right? Okay, radioactivity. Can someone tell me what radioactivity is? Go ahead.
Atoms unstable material made of some atoms that is split and not sent off.
Okay, let's try this. It's the emission, no, let's do better. It's the spontaneous emission
No.
of particles. But there's one key part you're missing from the nucleus, not just from the atom. Atoms can emit all sorts of very low level, low energy stuff, and it's not a big deal. It's from the nucleus that's important. Okay? So, spontaneous emission of energy from now what does spontaneous mean?
Very fast.
Doesn't mean very fast. Nothing causes it, right? There's nothing that causes it to emit it. It's not like you bump the atom and it knocks something out, which is what unstable usually means. It means that by itself it will emit particles, right? Without needing any kind of instance. Which means that that emission is going to be controlled by what laws? Yeah, quantum mechanics, probability, right? So there's a quantum mechanical effect that allows things to happen. Probability. Oh, I just realized we're going to have to cover a few of the things to understand some of these things.
Oh no.
Boy.
It's okay, still don't need that. Relax. I wouldn't.
Sure.
I feel like Dr. Dog's gonna have extra correct questions.
So, okay, sorry, let me, I'm going to have to teach a few other things first, in order for you to understand. All right. What?
You're ready to play? There goes.
Right. So,
Spontaneously shut off.
Then it wouldn't be, if it were a ghost, that wouldn't be spontaneous.
What if it's really thought spontaneously?
I see. What if ghosts are radioactive? All right, moving on. Okay, I realize, wow. Okay, I think I know how we'll do it. Okay, let's talk a little bit about wave functions. You don't relax, it's okay. Come on, guys. It's not a trigger word.
It is.
I want you to imagine that there's a particle. It's trapped inside these barriers. Okay, walls will do. Okay. Now, the particle is a wave function. Right, as you might imagine, that wave function you would expect would be, inside this region, right? So when you're calculating the wave function, we're certainly not going to go through the math of that. When you're calculating the wave function, you get something that it ends up looking like a wave, maybe not so surprisingly, and there's a probability for being at some positions inside this little area, a box we usually call it. But here's the thing: when the wave function reaches the end here. It turns out when you look at the math, it does not, as you might expect, immediately drop to 0. Instead, it has an exponential fall. Now exponentials, as you know, fall very quickly, right? Like e to the negative x, right? But very, very fast. So it drops off like this, right? Going asymptotically to 0. I can't draw very well. But you know exponentials fall very quickly. Okay. But then, once it goes through the barrier, it is not at 0. Right? And now that it's through the barrier, it will continue its happy way. Right? Okay. And of course, the same sort of thing on this side. What that means is that the wave function outside of this box is not 0. And what does it mean if the wave function outside of the box is not 0? It means there's a probability that the particle would be found out there.
What are the peaks and the crests?
So that's a wave, right? So if you square it to get the probability of the position, right? So the probability of it being in a given position actually has more likely places and 0 points. Yeah. Okay, but the important part is that the probability does not drop to 0 when you go outside of the box. Okay, there is a probability that you can find it. Now, it drops with an exponential curve. So that means the probability will be generally small, right? But not 0. And in quantum mechanical theory, it doesn't matter how thick this is, how powerful the energy barrier is, how thick the wall is, it will never go to 0. It'll always be exponential. So it will drop, but exponentials never reach 0, right? So that means that when you have a particle, there is a small but non-zero chance that it will escape from any kind of box that you put the particle in. Okay? So, for example, if you have a particle heading at a wall like this, most of the time the particle will hit the wall and bounce off or get absorbed or whatever happens. But there's a chance the particle can do what? There's a possibility that the particle will go right here and then keep on going to the other side. And this effect whereby a particle can go through something it really shouldn't go through is called tunneling. Okay. Now the mathematical details of tunneling are kind of fun, but they don't reveal that much more about it. It's just that it's definitely an exponential behavior with the thickness of the area that needs to tunnel through. So therefore, you're not going to see tunneling very easily because the probabilities die off very quickly. Yes?
What's the difference between this and then my particle accelerated particles just going through different ways?
That's not tunneling, that's just going through. Because what this really is not actually a physical wall that matters, but it's an energy barrier. Okay? So what you have is a wall has electrons in it, right, that hold together into a crystal structure that repel any attempt to go through, right? So if you try to go through it, there's an energy repulsion, right? And so what's repelling my hand is energy. There's potential energy in the wall that keeps me from going through the wall, right? But if I push hard enough, what could happen? I'm restraining myself carefully because sometimes we do not know my own strength. So what can happen? It could, in fact, break through that energy barrier if I give it enough energy, right? If I apply enough energy, I will break through the energy barrier in the wall, and then I'll go through. So that amount of energy that it would take to break through the wall, that's really what this is, okay? It's how much energy do you need to make it through. So as a result, it's not about any particular, like whether it's a wall or what it's about the energy that would be need to get through it. Okay? So, wait, what was your actual question?
It's like, what is different about tunneling? Like,
Right. So, if you have a high energy particle in the collider, those things are, all the crystal structure of the things are like a billion times less energetic than the particle itself. So, there is no energy barrier. This is the energy barrier the particle's up here, you know? So it just goes right through everything. Okay, it's not tunneling through, it's just blasting through. Okay, tunneling is not forcing your way through. It's going through when you don't have enough energy to actually make it through, right? So you have a wall here that would require, you know, to break through the wall requires, you know, 60,000 joules of energy to make through, for example, right? And you have a particle coming in with 300 joules, so it shouldn't make it through, right? It should just stop. But there's a probability that it can go through anyway. A result of this, in quantum mechanics, you basically can't trap things anywhere. There's always a possibility of it getting out. And there's very few things that have zero probability in quantum mechanics. There's a few things, because you can get the wave function to zero at certain points. But in general, most things have a probability of happening, even if a very small one. Because the probability is basically never drop to zero, they only go down exponentially. There's a few things that are forbidden, like speed of light stuff, you can lock that one out, right? But most things you can do it. So when I was in college, I played a lot of foosball, and I remember a friend of mine who played, and he was not particularly good, and so he was hitting the ball into the goalie, and then it would bounce off, and he would hit it again. And after about 5 times, I'm like, you know, Steve, if you keep hitting the ball into the goalie, I don't think anything's going to change. And he responds, no, there's a small but non-zero chance that it might tunnel. Right? which is technically true. That is technically a true statement. Actually, for an independent study, once as part of it, I had some kids calculate the odds of a sort of macroscopic tunneling effect happening. So some kids, I remember, did the odds of a car tunnelling through a brick wall.
Oof.
And with those parameters that we set up, we calculated it, and the odds of it were 1 in about, we had to do some approximations because the computers weren't good enough to get the numbers as high, so we had to do it ourselves. But it was 1 in 10 to the 10 to the 500.
That's pretty high.
Yeah, so not great odds, right? But they're not zero, and so it is true that there's a small but not zero chance that all the atoms in the Earth will spontaneously rearrange themselves into a duck. But very unlikely.
But you're saying it could happen.
Yeah.
I want to be spontaneously.
What did you learn?
nuts.
What did you learn at your science school? Oh, you know.
We could be spontaneously rearranged into a duck.
Okay. So now this might seem like because the probabilities are so low, this might seem like kind of a useless little effect. It turns out it's not a useless effect. It's an extremely helpful one in certain applications. In particular, there is a piece of equipment that relies on tunneling to work. It allows us to make the smallest, the most sensitive microscopes there are, which are called. Anyone know the full name? The Scanning Tunneling Electron Microscope. Right? STEM. So now STEM means something else. For the record, science, technology, engineering, and math is not a subject. It's 4 subjects. Right?
Wow.
That's what it's STEM subject.
And it's not quite clear what technology means, like using your iPhone. And like they are not one subject. Anyway, sorry. So the scanning tunneling electron microscope works like this. You take a very thin, narrow metal tip. Okay, and they can make these things really thin with modern machining techniques. They can make them they can get them down to like a few atoms across apparently at the tip. And then you have something you want to know what it looks like, right? So what you do is this thing has to be metal for it to work. So when they're doing biology ones, they put on a special process like coats it in metal. Okay? They have a special thing that basically puts an atom thin layer of coating of metal on it. And then what you do is you just take this and you move it across. You scan. Okay? You move it across it. And it does not touch it, because if you touch it, you break the tip. So it doesn't touch it. Instead, as this moves across, this thing's made of metal, and what you are doing is you are measuring, you connect this thing to an ammeter. You're measuring the current in the metal. Well, the current in the metal should be 0. But when you get it close to another piece of metal, what can happen? The electrons from here can tunnel through to here, and then you can read it out as current. And what determines the rate of the electron tunneling? The distance will determine the rate at which they tunnel. So the farther away, the lower the tunneling rate. The closer it is, the higher the tunneling rate. And so what you do is you move this thing across, and the rate of the current you get will be higher and lower. It'll be extremely small. But it'll get higher and then get lower and then get higher and then get lower. And from that current, you can reconstruct what is the shape of the thing you're going over. And then you just go back and forth. You go this way, back and forth, and go this way, back and forth, and you can reconstruct a whole picture of something extraordinarily small, which is how you get those pictures of nuclei and mitochondria and stuff like that. It's by using a scanning tunneling electron microscope. Okay, so tunneling is actually a thing. We actually use it. It actually works. We've never actually seen anyone throw a ball through a wall, and odds are pretty good we never will. But when we're talking about an electron across a gap of a micron, that's something that can happen. And so this is this is like a real thing. Tunneling. Yeah. That's why you go slowly, right? So that you can have enough statistics to be pretty sure that So you wouldn't do this with like one electron, right? You would do this with like 1,000,000 electrons, and then you're like, okay, I'm pretty sure that this rate is trustworthy. And 1,000,000 electrons is not a lot, right? So, okay, good. So now we know what tunneling is. And the reason for that was because we need to talk about where radioactivity comes from. Okay, so where does radioactivity come from? A lot of different things, it turns out. So let's talk about radioactivity. One thing is it's completely random. And so what completely random means is that atoms do not get old. Okay? In other words, you're an unstable nucleus, right? So you're gonna emit some particle through radioactive decay. Because you're emitting a particle, the nucleus will have to change when it emits it, right? Because of conservation of energy. Well, they call it radioactive decay. So you don't get old, though. In other words, you've lived 100 years without decay. Your odds of decaying are the same as they were if you were just born yesterday, right? There is no age here. It is a completely random process. That completely random process can be modeled by a formula that I gave you before. You remember this? It's not half-life, it's lifetime, but it's the decay rate of the particle, right? This is, right, remember this? We use it for muons. We put it in the accelerator project, right? This is how many, you start with this number, this is how many numbers you end up with, and tau is called the lifetime. The lifetime is the amount of time it takes for the number of particles to drop to 1 over e of the original. That makes perfect sense when you look at the equation, but it's a little bit harder for people to imagine, so we often modify this to a version that looks like this. Okay, instead of making the base e, we make the base 2. And then this thing here, T1/2, is called the half-life. Okay, and that's the amount of time in which there is a 50% chance of decay. Which means if you have a bunch of particles in one half-life, what will happen? Half of them will decay. Oh, I forgot. Oh, okay. Sorry, I just got it right this year. Maybe this decade has been not great for me. So it's the amount of time in which you have a 50% chance of decay. Okay, good. So that's how we measure things, by half-life. Now, different particles have different half-lives. Some of them, they can be as long as hundreds of thousands of years, and as short as fractions of milliseconds. And it depends very much on the particle itself. But that's when we say something is unstable, it means it will undergo some kind of decay. Now, the forms of radioactivity, there are how many? 3, good. There are 3 big ones. They were discovered well before we knew anything about atomic structure. And so their names predate all the other names. Okay, now we know what they are, the time we did it. So we have these old names for them that are still in use because they've been used. So we made a little chart. There is, first of all, alpha decay. The particle that is emitted was called an alpha particle. Turns out to be a helium-4 nucleus, which is to say 2 protons and 2 neutrons. Okay. It's a helium-4, the nucleus of a helium-4 atom. Okay, 2 protons and 2 neutrons is what an alpha particle is. The source of it, like where it comes from, is, well, you think of it this way. Think about the energy as you get near the nucleus of an atom. Let's say you're a positive particle. You are getting near the nucleus of the atom. What does the nucleus do to you? It pushes you away because it's positively charged, right? So as you get near to it, you'll get more and more repulsive energy, which is positive, okay? So it repels you. It's positive energy. It's more and more energy pushing you away as you get closer and closer, right? It's an inverse square law, it turns out. But you do know that when you get really, really close, what happens inside the nucleus itself? The strong force can take over if you get close enough, right? And so at that point, what happens? Suddenly you get pulled into the nucleus, right? So what happens is at very, very short ranges, there's this drop, right? And here is where the nucleus is. right? This is where the particles in the nucleus live, in this little thing here. This big thing here is referred to with this great name. It's called the Coulomb blockade. Okay, and it's this big energy barrier, which is what keeps the particles in here and keeps all the other particles out, right? Because this thing is enormously high in terms of energy, right? It's this giant energetic wall that you can't like, get through, and that's why that's in the nucleus. Now, some atoms, like hydrogen or something, or not hydrogen, really, helium or something, have things look like this. That say it's down here to a negative energy, which is totally fine. It just means an attractive potential. Okay, this is actually most atoms look like this, but there are some atoms that instead look like this. It's still trapped behind a giant web, but what do we know about trapping things behind a giant wall? You can't keep them trapped there all the time. What can they do? They can tunnel through, and once they're here, they can fly out. Right? Right. Now, if it really goes down into the negative energy region, which means attractive energy, then this doesn't happen. So that's why it only happens with some atoms. The some atoms have it here where it's basically stable, but there's always the possibility of tunneling. So the source of alpha radiation is tunneling. Now, it might seem like if you were tunneling, you would just have individual protons going through. And it seems like that to me too. Apparently the nuclear physicists say that it's all about energy, right? Getting the lowest possible, and atoms always want to go to lower energy. And apparently it's energetically favorable to go out as a whole clump of protons and neutrons, actually reduces the tunneling probability quite a bit. Increases the probability of tunneling quite a bit. And so they tend to come out in a clump, or they always come out in a clump of protons and neutrons, because that's easier to do.
Is tunneling magical, or is there an analogy of like temperature? Because the temperature is an average kinetic energy, but some of your particles are high enough energy that, say, if you had a barrier, you could spontaneously have a very high energy particle that could break through the barrier.
Right.
Is it similar to that, or is tunneling entirely different?
There are analogies you can draw like that, but at the fundamental level, it's entirely different. There is no classical analog to tunneling. You can use analogies like that to understand parts of it because it's a statistical effect, right? But tunneling, but with temperature, it's just they all have different properties, right? With tunneling, it's the wave function never drops to zero, and so there's a probability of it being basically anywhere. So sometimes it is, right? But that ability to go places you shouldn't be is a purely quantum ability. There is, by the way, a reverse version of tunneling. Tunneling is that you hit a wall and you keep going through, right? There's the reverse version of it. We don't have a name, but you could also have something where you go to the edge of a cliff and you bounce off. You also have that. That's the reverse version of tunneling. I don't know what the name of it is, but you can do it both ways.
Relativistic speeds.
Yeah, kind of weird, right? Okay, so let's think about alpha particles, how they are. Notice, do they have charge?
No. Or yes.
Yes, they have charge +2. That means they'll interact electromagnetically, right? Mass-wise, they are, compared to, say, an electron, very heavy, right? Okay, so they're massive and they're charged, meaning they'll interact easily, right? So when you shoot them into something, they interact very easily and very quickly. And so if you have, the analogy is often used as a pinball machine. You guys know what those are? Yeah. Okay, when you have a pinball machine, if I said a photograph, you'd be like, what? Like an 8-track or something? So if you have a pinball machine, then it would be like taking the pinball machine, and instead of shooting it a pinball, you shoot it like a big lump of silicone. Right? It goes, right? In other words, it stops right away, expending all its energy right away. So the distance of penetration of these particles, like how far it will go, is like, it's basically stopped by paper. Okay, in other words, a sheet of paper is sufficient to block alpha particles. So these things are real easy to stop. But when they do stop, they deposit all their energy at once. These guys are high energy compared to regular scales. They're not high energy compared to colliders, okay? But they have NeV level energy, which compared to normal things is crazy high. And if one of those hits you, it is not super good for you. But think about it, with an alpha particle, if you have an alpha source right here, is it a big deal? It's not. It's not the air. When it hits you, what will it hit? Your skin. And what's the top layer of your skin made of? Dead skin cells, right? So it hits only dead skin cells and you're fine. However, alpha emitter could do you damage if you don't have any skin, right? There are other things to worry about now. If you don't have any dead skin, that's not how it works. Your skin cells die.
Shave it off.
No. If you, and you did well with it. Oh, yeah, exactly. If it got into you, if you ate it, much bigger problem. Because now when it does hit the stuff, it does a lot of damage to whatever it hits. So damage to dead skin cells, no big deal. But if it's inside of you, if it gets into your bloodstream, then it does damage to your whole body. In fact, the body brings it around carefully so that it can damage every part of your body, right? Like up close. And then it does a lot of damage. So alpha emitters are fine unless they get inside you, which can happen either if they form a dust, like plutonium does, or if they if you end up eating them, like those old Fiesta-ware plates. Yeah, Fiesta-ware plates, not anymore. Used were these bright orange plates that were made with a thin coating of uranium oxide that if it gets into you is not super good for you, so they stopped making that. Yep.
This technically be considered a biological weapon if we weaponized this.
We typically refer to this as a radioactive weapon, which is still a weapon of mass destruction.
All right, that works.
But I mean, it definitely hurts biology. Okay, next time is beta, of course.
Well, I mean, like,
Positron.
it works very much the same.
Beta emission turns out it comes from it turns out to actually just be an electron, occasionally a positron. Doesn't really matter.
Oh, I was lied to.
Okay.
These things are.
The source of it is actually one we know. We've actually done the diagram for it. It's neutron decay.
Oh.
Wowie.
Right? It looks like here. Go ahead. This is a neutron. This is a proton. How do we draw the diagram? Connect these and then what? And then hit a W minus, so that decay to an electron and an antineutrino.
Look
right?
at that beauty.
Okay? So this diagram is referred to as beta decay because it's a source of beta emissions. A neutron in the nucleus decays to a proton plus an electron plus a neutrino. The proton stays where it is. The electron goes out, so does the neutrino, but no one cares about neutrinos. So the electron is what we see, right? So the source of it is beta decay. Now, compared to an alpha particle, what's an electron? It's negatively charged. It could be a positron too, but it's much less massive, much less massive, right? And so that one compared to the alpha particle is like taking a pinball machine and putting a pinball into it. And it'll bounce around for a bit, lose energy and stop, right? As a result, they usually say the rule of thumb is this is stopped by plywood. You know what plywood is, right? That thin pressed wood. Right? So a piece of plywood would be enough to stop beta particles. As a result, beta particles near you can actually damage you. Right? They go through enough layers to actually deposit some serious energy below the skin cells layer and thus can actually damage you. So they are more concerning. Also shouldn't eat them. Also
Shouldn't really eat anything. That's just kind of.
You shouldn't really eat anything.
Do you have some issues you need to talk about?
I don't like eating, but no one.
The effect of this, by the way, is it's going to go. This is going to lose 2 neutrons and lose 2 protons, right? With beta emission, what's it do to the atom? It loses a neutron and gains a proton, changing the atomic number up, which is interesting. Okay. Now, the next type is gamma, of course.
Dun, dun, dun.
All right. The particle of a gamma turns out to be the particle we call gamma, which is the photon. That's why it got called gamma. It's nothing to do with Einstein. It's because it was a gamma ray. That's why we use the symbol gamma for it. Okay. This one comes from nuclear excitation. I'm not going to go into detail on this right now, because I'm going to cover atomic excitation later, and then it's the same thing as nuclear excitation. If you took AdChem and you did the spectroscopy in AdChem with the lines and stuff, we might do that. We can do that briefly in here, not just quickly. But if you did that, it's like that, but with the nucleus instead of with the electron shells. basically what happens is it gets into a high energy state, and then it drops down into a lower energy state, and that leftover energy gets radiated in one giant photon. Sort of like the difference between, remember the delta plus particle, which is the same as the proton, except with a different spin and a different mass. Well, the delta plus particle can decay to a proton, makes sense, and that the difference in energy will all be released in a giant photon. Okay, it's not a big photon; it's a very high energy photon. So gamma rays, as you've probably heard, are very, very high energy photons, way beyond the regular X-ray stuff, way beyond anything else. They're very, very high energy. And what's their mass? 0. And what's their charge? 0. And so they don't interact nearly as readily as an alpha particle does, and they're much harder to stop because because without the mass, you just kind of plow through things. So that's like taking a pinball machine and shooting a gun through it. Right? It just kind of keeps going. It does damage and then just keeps going, right? So gammas are your bigger problem. There's a gamma ray source in the room. You should be concerned and then leave the room. You shouldn't exactly, it's not exactly a great idea to eat them, but it kind of doesn't matter. So, well, because
It will affect you nothing.
they're usually stopped by lead. Usually about an inch of lead is what they say to really stop them, though a thinner amount will usually say lead. Anything dense, of course, will do just as well. Lead is particularly dense, so people use that one a lot.
My brain.
But tungsten is dangerous and toxic, remember that. Yeah.
So what would you wear for like a hazmat suit? Like
What do hazmat suits do? Hazmat suits are good against alphas and betas.
Okay.
They're not going to help against
I was
gammas.
gonna say,
There are radiation suits that are lead lined. Okay. They often give you those vests when you get an X-ray. Like a dental X-ray, they'll get you the vest. The vest is very heavy. That's because there's lead in it. It's to absorb any stray X-rays that come out, right? So they're not irradiating other parts of your body. It's precautionary. The amount of radiation you get in an X-ray is not a lot to worry about, as long as you don't do it a lot. Also, that's why X-ray machines are always designed so that the switch to operate them is way away from the machine. That's requiring the worker to be very far away from the X-ray source, thus they're not irradiating themselves all day. The effect this has is 0. All it does is release energy. It doesn't affect the nucleus composition itself. Okay, gammas are a bigger problem. You should avoid them. Dodge. So those are the basic types. Now there's one more I'm going to mention, even though it's not one of the six, so it doesn't have a Greek letter. They mentioned delta rays, but they're basically just gamma rays. They're with positrons and electrons, so they're not really any different. But there is nuclear physicists worry about that, but we don't need to. But there is another kind of radiation that does not come up very often, very rarely, but we can make it happen. And that is
The radiation of
neutron radiation. The particle for neutron radiation is, good job.
How are you?
The source of neutron radiation we'll talk about in a moment. Neutrons have a mass that is high mass, good. Their charge is 0. So because of the 0 charge, they do not interact well, right? They're like those hadrons we've dealt with in the hadron. Remember that? The electrons and photons interacted in the econ, right? That's these guys. They interacted in the econ. What do the neutrons do? They plowed right through and needed a lot of stuff to stop them, right? Okay, so that's what neutron radiation is. And so these guys, if you ever make them, they're stopped by several meters of concrete. It is hard to stop a neutron. Oh, well, you know how hard it is to stop a neutron. You need, if you want to stop 99% of them, you need like 40 interaction lengths, right? Remember that? So that's a lot. And you know those interaction lengths are long, right? So you need a lot of material to stop a neutron. Which is why, the primary reason why we have to build all these detectors underground, right? Cosmic rays, the shielding from cosmic rays is a nice benefit, but the main reason is safety. You have to put them low enough underground that no radiation is going to get out of there, because we produce neutrons in these things, and neutrons are bad. But what else produces neutrons? Well, now's the beginning of a fun story.
Oh boy.
let's suppose we take some uranium. Okay.
And we're going to stick it down right with it. Have the two pieces here.
If you take a chunk of uranium, okay, use the symbol for uranium, and let's say you hit it with a neutron.
Oh.
Well, what do you suppose happens?
Not good
No,
thing.
it's nothing so simple as that. What do you think the neutron does? Well, the neutron, is not repelled by the Coulomb blockade. It's chargeless, right? So it can go up pretty easily. So what do you suppose generally happens?
There's the uranium
It what? Yeah, it gets absorbed by the nucleus most often. If it actually hits the nucleus, it will typically get absorbed by the nucleus. Okay? Now, that's fine, and that can happen with a lot of things. Now, the resulting isotope that forms is often radioactive, which is not great. By the way, that's not a good thing, typically. But there's a particular isotope of uranium called uranium-235. Uranium-235 is, like all uranium nuclei are unstable. Uranium's an alpha emitter. Okay, the nuclei are unstable. If you hit a neutron into that, you get uranium-236, right? Okay. Uranium-236 is really unstable and is very hard for it to hold together when you throw out the neutron. You might get the neutron in the right place and then it holds together for a bit and then decays regularly, but more often you get the neutron in a bad place and it becomes too unstable and the nucleus is unable to stay together. Instead, it grows unstable, kind of vibrates and then pulls into two pieces and then kind of pop apart. And what you get is right away, then it rips itself into two other nuclei, smaller nuclei, for example, baryon and krypton, although it could be a variety of different things. And there's going to be some leftover neutrons from this ripping apart, and you'll end up with a few spare neutrons flying around like this. Okay? This one, because it takes one thing, then rips it into two. Borrowing a word from biology, we refer to this as fission, nuclear fission. Okay, it's from a Latin word that means to, I don't actually know what it means. It is, right, it means okay, so you can see where do we get neutrons from? Nuclear fission. Okay, does this ever happen spontaneously? Not really, sort of. There are elements that do this spontaneously, but they're man-made. So you can't find them already.
I remember reading that there was some readings I forgot where it was. I think it was Cameroon, but apparently like several 100,000 years ago there was an area in Cameroon where natural nuclear reactors still.
Oh, it's possible, yeah. Big uranium deposit or something to do that. Now here's the fun thing. The fun thing is that you can take this process, and what comes out of this process? Neutrons. But what went into the process? Neutrons. So we can calculate something called reproductive constant. The reproductive constant, K, is basically it's an average number, right? And it's the number of neutrons produced divided by the number of neutrons input. Like an average, it's an average number, right? And so what can you do with that? Well, you could actually set it up. What happens if K equals 1? What happens if K equals 1? Then whatever neutrons come out will hit another nucleus of uranium-235, which will then fission and produce neutrons, and then those will hit another nucleus of uranium-235, which will then fission and produce neutrons, right? And you will end up with this is called, this point is called the critical point. Okay, makes sense, right? And at this point, you can create what's called a self-sustaining chain reaction. And fission was borrowed from biology, but chain reaction is a physics word. We made that one up. Back in the old days when they made good names for things. Okay, you get a self-sustaining chain reaction. Now, the reason that's useful is because this does not only release the barium, krypton, and the neutrons, it also, some of the binding energy of that nucleus is going to be released. That is to say, the sum of these masses is less than this mass.
Oh.
So some of that mass energy, which is really gluon energy, binding energy, gets turned into other energies, into kinetic energy, right? And a good amount of it goes into gamma rays. Some of it goes into kinetic energy in these particles, other parts go into gammas. Okay? The gamma rays will shoot out, they'll get absorbed. When they get absorbed, what will they convert into? They are photons. What do photons turn into when they get absorbed? Like if you shine light at something, the light gets absorbed by it, and it gets what? It heats up, right? So this means heat, right? It converts itself into heat. So that means you release quite a bit of heat. Wow, what could you do with something that heats itself? You can have a chunk of uranium that heats itself without you doing anything. Well, you hit it with one neutron, and then you wait, and it heats itself. What could you do then? You can take a chunk of it and put it in water. Wouldn't that be exciting? Why? It'll make water, it'll make steam, it'll give you the steam. You put a turbine up here, and it turns the turbine, you connect it to a generator, and then you power these lights, because that's where these lights come from. Right? Most of the power in Illinois comes from this.
Yes.
Right? This, of course, is a nuclear power plant. Right? And nuclear power comes because that's all it is. There's water, at the heart of it all is just water and a chunk of uranium. Now, the thing about the uranium is that you do not just take a chunk of uranium. Uranium-230, the standard uranium has a half-life of like 40,000 years, something like that. So it's not going to do this by itself. Okay? But the one that you need is the uranium-235 isotope. Unfortunately, that is not, or maybe fortunately, that is not the primary isotope of uranium. The primary isotope is uranium-238. Uranium-238, if you hit it with a neutron, you know what you get? Uranium-239. That's it. Not helpful. Okay? So the only way you can get to a criticality point, see, here's the thing. So do you know what the abundance of uranium-235 is in nature? It's about 0.1%. So if a neutron happens to hit a thing of U-235, great. It fissions, it releases more neutrons, they hit the 238 atoms, and then nothing happens. So the only way to create a chain reaction is to do what? Is to what? You need a lot of U-235 without the other 238, right? How can you do that? You'll have to take your uranium and what's the word for it? Enrich it. Enrich it. You'll have to enrich it, which means to increase the proportion of U-235 in it. Now, that's hard to do. U-235 is chemically identical to U-238. They have the same electron shells. The only difference between them is mass. The only difference between them is mass. It's a very small difference in mass. So we have a device for separating things by mass. Use it in biology. It's a centrifuge, right? So what you do is you take uranium and centrifuge it to make a difference of 3 out of 238, which is not a very big amount, right? Basically 1% mass difference separated by uranium atoms. By the way, how big do you think a centrifuge would have to be to separate uranium? Pretty big. Yeah, pretty massive, it turns out. And so these centrifuges, so when they first came up with this idea, they're like, to produce this kind of uranium, we would need like a square mile of factory just of centrifuges. But it was wartime, so they told that to the military. They're like, okay, good, we'll start building it tomorrow. And that was the origins of Oak Ridge National Laboratory. It was originally just centrifuges. And they're like, even with that, it'll take like a year. And it's like, well, we better get going. And so that's what they did, right? In Germany, by the way, which was working on it, which had the same physics, was working on the same thing. They're like, wow, that's impossible. And in Japan, they're like, okay, well, I guess we don't have to worry about that because there's just no way to enrich the uranium. And in America, it was like, all right, let's do it. It wasn't like we were smarter. We have a lot of space, we have a lot of people, lots of steel. need steel to build the centrifuges, and that's all they did. So the way you do it is you have to run them through sequentially. So you put it through the centrifuge and it enriches it a little bit, and then you take the outer part and then centrifuge it again, and you chain it like 20,000 times or something. So it's a very, very slow, very expensive process to enrich uranium. To get uranium to work in a reactor, you need to get it to approximately 20%. Although I think you can maybe work with even 5%. Okay, and that's what they call enriched uranium. Then you can put it in a reactor and then it works. So those reactors, so we have those things still working because that's what makes the fuel rods for our reactors, and we use those to power our country. Now, as you may know, and the first time this was ever done was where? University of Chicago, in a squash court, right? And they had to do this. They had to assemble a bunch of iron, lead slabs as shielding, right, and then uranium as fuel. And you can't tell anyone what you're doing, right? So you can't bring in big construction equipment, right? Because they're doing it very secretly. And who is it that's working on all these? Physicists. So like IMSA students. So imagine you tell all the IMSA students to move around a bunch of lead blocks. So what they did was they paid the football team to move the lead blocks for them. And just, they were paying them and said, don't ask questions, moved all these boxes.
You're training. You're getting paid to move
actually, that was the idea. It was like, they're like, okay, it's like weightlifting, right? Okay, sure. And so the football team assembled the reactor for them. And they're like, move that there, go drop it. And the first sustained chain reactions took place in the squash court at the University of Chicago. The squash court's no longer there, but there is a statue commemorating the spot in the University of Chicago.
After the nuclear reactor.
And the person who was in charge of that was Enrico Fermi. Enrico Fermi, who when he died, he was a professor at the University of Chicago. When he died, they named the lab after him. Because there's many, many great contributions to nuclear particle research. So there's one little sequel to this. Okay, it's not a sequel because the thing is, when people came up with this idea and realized, oh, by the way, what's the mass difference between all the products and U-236? So what percentage of this mass has to get released into energy? Approximately 0.25%. Now, if you remember your equations, in SI units, 0.25%, say 0.25 of a kilogram, is how much energy? How do you convert that to energy? What do you multiply by?
C squared.
C squared, which is not equal to 1 anymore because we're in SI units. So how much energy is this? That's quite a lot of energy. So immediately upon realizing this, the person who's credited for first really making the gap, is the leap there, is a physicist named Leo Szilard. And when Szilard realizes this, the first thing he says is, oh my goodness, this could be like a limitless clean energy source. I am of course joking. What is the first thing he says? Oh my goodness, we could blow up so much stuff with this. There's an interesting story where he publishes a paper. He sends in a paper, and he's like, oh shoot, this could be a bomb. I don't think I want the Germans to read this paper. So he sends a thing to the editor saying, never mind, don't publish the paper. And then he says, then he does more calculations, someone else's calculations. He's like, oh, never mind, this mission thing's not going to work out after all. So he sends another note that says, it's okay, go ahead and release the paper. And then someone else does a calculation that makes them realize that it can happen after all. He's like, crap, don't publish the paper.
By which point the paper was published.
The paper did not get published until later. But I mean, it was cat was out of the bag. Anyone could defeat. It's not like Germany had no physicists. Although all their best physicists were Jews. All the best physicists were Jews. And what did they do with the Jews early on? They bar them from university jobs. That's one of the earliest things, was to not allow much work in their universities. Stupid move. What did they do? Because this was early on, before Holocaust stuff got bad. What did they all do? They all left. And later on, when things got rougher, they escaped. Right? Niels Bohr escaped Germany. Right? He went to a conference and never came back. That was arranged, of course, by the United States, who said, oh my goodness, you can't live in Germany? We've got a place for you to live. It's called Los Alamos, New Mexico, and you'll love it. So, as we promised, we will not discriminate against anyone here. So, and this is part of the story, an interesting sidelight. And so the point is, racism loses wars. Be careful. All right. So that's. We will go into more on that on Monday. About the interesting case on
What do you think?
I didn't hear what you said. I was very.
I'm like, I don't know. We locked up a lot of Japanese people during World War II.
That was the joke.
Okay, but we didn't lose the war.
No, the thing is, Germany in World War II.